Okay, in this module, we're going to be looking at the third expression for E star of S. Just to recap, we looked at two expressions for E star of S. The first one gave us a relationship between the Z transform and E star of S. We said if I take E star of S and replace E to ST with Z, I'm going to be getting the Z transform of the signal E that I sampled at the output of the sampler. The second expression, we use the calculus of residues, and we said that the multiplication in the time domain is convolution. We get this complicated convolution integral, but we said if we use the calculus of residues, this will simplify to the summation of the residues multiplied by 1 minus e to t s minus lambda I, where lambda i's are the poles of E of lambda. Now this integration or this simplification applies only if we have finite distinct poles. If E of lambda has finite distinct poles, otherwise the expression is going to be much more complicated. Now what we're going to do is we're going to get a third expression for E star of S. So starting with the second expression that we have here, we said E star of S is the Laplace of the multiplication in the time domain, which is going to be the convolution in the frequency in the S domain, E of S multiplied by delta T of S. And this is going to equal to 1 over 2 pi E of lambda delta T of S minus lambda. And if I do the calculus or using calculus of residues, I'm going to get another expression, which is the summation over I, the residue Ci of delta of T of S minus lambda I multiplied by E of lambda I. How is this different than the one we had before? So before, if I, going back, I had the residue Ci of E of lambda, and then multiplied by delta of T minus lambda I. Here, rather than taking the poles of E of lambda, I'm going to take the poles of delta T. Is that, hopefully that is clear. So in here, again, in here, I took the poles of E of lambda to calculate this integration. I took E of lambda, I took the poles, and we said this is the expression for E star of S. In the third expression, rather than taking the poles of E of lambda, I'm going to take the poles of this term. So in the previous one, I took the poles of E of lambda. In this expression, I'm going to take the poles of delta of S minus lambda. So that is going to give me, by the same logic that we did by using the calculus of the residue, is going to give me the summation of the residue Ci of delta of S minus lambda I multiplied by E of lambda I. Now this Ci is coming again from the residue of delta, not from E of lambda. Okay, so how do we simplify this expression? So to simplify it, let's calculate what this delta T is. Delta T of S. So we know that delta T of T is equal to the summation from n equals 0 to infinity delta of T minus n multiplied by T, which is delta of T plus delta of T minus T, etc. And therefore, if I take the Laplace transform, delta T of S is going to equal to the Laplace transform of this, which is going to be 1 plus e to minus st plus e to negative 2 t multiplied by, let me keep it, e to negative t multiplied by s, e to negative 2 multiplied by ts, etc. And we said in the previous module, if the magnitude of e to negative t multiplied by s is less than 1, then this series will converge to delta T of S that is equal to 1 over 1 minus e to negative t multiplied by s. So therefore, what we want to do is we're going to simplify this expression. So looking at the residue of delta of t of s minus lambda, delta t of s minus lambda is going to equal to 1 over 1 minus e to negative t multiplied by s minus lambda. Now what we need to do is we need to find the poles of this expression, similar to how we found the poles of e of lambda. Now we're going to find the poles for delta t of s minus lambda. So what are the poles of delta t of s minus lambda? So what we want to find are the poles of delta t of s minus lambda. And since delta t of s minus lambda is equal to 1 minus 1 e to negative t s minus lambda, we can easily find the poles. We want the denominator to equal to 0. Therefore, 1 minus e to negative t s minus lambda has to equal to a 0. This will give me the poles. When does this occur? If e to negative t multiplied by s minus lambda is equal to a 1. And that will occur if negative t multiplied by s minus lambda is equal to j multiplied by 2 pi multiplied by I, where I is 0 plus minus 1 plus minus 2 plus minus 3, etc. So if t multiplied by s minus lambda is equal to j multiplied by 2 pi multiplied by any integer, this is just integer, then e to j 2 pi is equal to a 1, and therefore I'm going to have a pole. So therefore the value of lambda when negative t multiplied by s minus lambda I is equal to a j multiplied by 2 pi multiplied by I. Okay, so therefore lambda I is going to equal to s plus j multiplied by 2 pi divided by t multiplied by I. Again, this I is just a constant. So if I divide by t, this is going to be j 2 pi divided by t, and then I move the lambda to this side, I move the s to the other side, I'm going to get lambda I equal to s plus j 2 pi multiplied by I, and I can write this as, just to simplify it, to simplify the expression, I can write this as s plus j multiplied by omega s multiplied by an integer. Again, I is 0 plus minus 1 plus minus 2, etc. Okay. Now if I look at this expression, I realize that delta t of s minus lambda has an infinite number of distinct poles. Delta t of s minus lambda I has an infinite number, this goes all the way to infinity, has an infinite number of distinct poles. And therefore, in order to calculate Ci, the residues, we can do the following. Since lambda I are distinct, we can calculate Ci using the following. Ci is going to equal to n of lambda divided by d prime of lambda, where lambda is equal to lambda I, which is equal to s plus 2 pi divided by t multiplied by I. Where is this coming from? So if you look at the module that we just had, at the end of this module, I had an appendix. I added these 2 pages at the end of the module. And what this example says, if I have an expression, if I have any function e of s, and I want to do a partial fraction expansion, and I have distinct poles, I can do the partial fraction expansion. I can calculate this C1 or Ci by multiplying s minus pi and evaluating this when s is equal to pi. This is how we calculate the residues when we do partial fraction expansion. This is what we know. Now, another way of doing this is, in order to calculate Ci, is by just calculating n of s, the numerator, divided by the derivative of the denominator, and evaluating this at pi. Both of these will give me the same results if I have distinct poles. Does that make sense? So this Ci equal to n of s over di, and I have the proof here. You can look at it and read it. So another method of calculating the Ci's is just by taking n of s divided by d prime of s. And again, this is, assuming this, we express this as equal to n of s divided by d of s. Okay. So continuing or using that, we can say that Ci is equal to n of lambda divided by d prime of lambda, the derivative of d, when lambda is equal to lambda I, which is equal to s plus j, there's a j missing here, j multiplied by 2 pi over t multiplied by I, where in this case n of lambda is just equal to 1 and d of lambda is just equal to 1 minus e to negative t multiplied by s minus lambda. And therefore, d prime of lambda is equal to negative t e to negative t multiplied by s minus lambda. Again, this comes directly from this to calculate the residues, and this assumes that n of lambda divided by d of lambda is equal to 1 over 1 minus e to negative t multiplied by s minus lambda. Okay. So therefore, let's calculate these values. So therefore, Ci is going to equal to 1. From here, we want to calculate n of lambda divided by d prime of lambda. So 1 divided by the d prime, which is negative t e to negative t multiplied by s minus lambda. And we have to evaluate this at lambda equal to lambda I, which is equal to s plus j multiplied by 2 pi divided by t multiplied by I. Okay, what is this equal to? We can simplify. If I substitute for lambda, this is going to equal to 1 over negative t e to negative t, and then I'm going to have s minus j 2 pi divided by t multiplied by I. I just plugged in lambda to calculate Ci. And this is going to equal to 1 over negative t e to j 2 pi multiplied by I. T with t is going to cancel, s with s is going to cancel. Let me cancel. This is going to cancel with this, t is going to cancel with t. I'm going to end a negative, is going to become positive, 1 over negative t multiplied by e to j 2 pi multiplied by I. And what is this going to equal to? This is going to equal to negative 1 over t. So therefore, the residue that I'm going to get is going to equal to negative 1 over t. So what I'm going to do, I'm going to go back to my expression here and say, okay, this is going to equal the summation of the residue Ci, but the residue that we calculated is just going to equal to 1 over t multiplied by E of lambda. So therefore, this is going to give me E star of S is equal to negative the summation over I. The residue that we just calculated is going to be 1 over t multiplied by E of lambda I. And since lambda I is equal to S plus j omega S multiplied by I, where I is equal 0, plus minus 1, plus minus 2, etc., we can write this E star of S is going to equal to 1 over t, the summation from I equal to negative infinity to infinity, and if I plug in for lambda I is going to be S plus j multiplied by omega S j multiplied by omega S multiplied by I, where I is 0, plus minus 1, plus minus 2, etc. And this is the third expression that we want to derive for E star of S. And what this expression says is that E star of S is equal to 1 over t multiplied by the summation of E of S plus j omega S multiplied by I. Okay. Now I know the derivation, especially because we did not cover the calculus of residues, we skipped. So I mean, there is some grain of salt that you have to take with all this derivation. And I know the derivation is also not straightforward, it's not very intuitive. So if you are a little bit, confused, please go back, try to follow a step by step. Again, we did not go into too much details. At the same time, we did not just write the expressions for E star of S. I think the book just write the results of all this without doing any derivation. So we try to go middle way between, going too much details and just writing the expressions without any background as to where they came from. Okay. Now, before the next thing, we're going to look at some properties of E star of S. But before we do that, anybody who's looking at this expression, this should look familiar. Where is this expression coming from? It's coming from the sampling theorem. When we covered the sampling theorem, if you remember, if I have a signal that is band limited, and this is the spectrum of the signal. If I have a signal, this is the signal in time, and this is the frequency. If the signal is band limited, if I come and I sample this band limited signal, what is the spectrum of the sampled signal gonna look like? If you remember, the spectrum is gonna look something like this. This is gonna start repeating from negative infinity to infinity. Hopefully you still remember this. When we sample the signal, we're gonna get duplicates of this spectrum repeating every omega s. This is at omega s, this is at 2 omega s. And if you remember, we said if omega s is twice the maximum frequency of the signal, then there is not going to be aliasing. If omega s is less than twice the maximum of the signal, then these are going to start overlapping. And of course, this is going to be scaled by 1 over t. And this is, again, coming directly from the sampling theorem. Now I have in the homework, I have an assignment for you to try to get this derivation from the frequency domain, from the sampling theorem. Try it. You don't have to turn it in. I'll give you the solution later on, but please look at it. So again, even though we derived this using the residues and the calculus of residues, you could have also gotten the same results directly from the sampling theorem. We already know these results from the sampling theorem. The sampled signal here is going to have a spectrum that is going to be the repetition of the original spectrum, and is going to be scaled by 1 over t, repeating every omega s from negative infinity to infinity. Okay. Okay. So let's look at properties of E star of S. The first property is that E star of S is periodic. In S with period that is j omega s, and that is to say E star of S plus j omega s multiplied by any integer is going to equal to E star of S, and this is j for m equal to 0, plus minus 1, plus minus 2, etc. Okay, let's prove this, that E star of S is periodic. Since E star of S is equal to the summation from n equals 0 to infinity E of nt e to negative nt multiplied by S, if I were to calculate E star of S plus j m omega s, this is going to equal summation from n equals 0 to infinity e of nt e to negative n t multiplied by s plus j m omega s. So we just plugged in, instead of s, we plugged in s plus j m omega s. Now I can write this as the summation from n equals 0 to infinity e of nt e to negative nt e to negative j n multiplied by m multiplied by t multiplied by omega s. Okay, now what is this e to negative j multiplied by n m t omega s equal to? I can write this as e to negative j n m multiplied by t multiplied by 2 pi divided by t, and therefore this is going to equal to e to negative j n m 2 pi, which is going to equal to a 1 for any value of m and n. For any m, or for all mn, and therefore if this is equal to a 1, then we got what we're trying to prove, which is e of s plus j multiplied by m by omega s is just going to equal to E star of S, which is equal to the summation from n0 to infinity e of nt e to negative n multiplied by t multiplied by s. There is an s missing here. Okay. Okay. Now why is actually, before we just on the side, where is this coming from? Because we know e to j theta is equal to cosine theta plus j sine theta, and therefore e to negative j n m 2 pi is gonna equal to a cosine of negative n m 2 pi plus j sine negative n m 2 pi. And what is this gonna equal to? If n and m are integer, this is just gonna equal to a 1, and this, the j sign, is gonna equal to a 0. Okay. The second property is that if E of S has a pole at S equal to S1, then E star must have poles at S equal to S1 plus J multiplied by M multiplied by omega S. So if E of S has a pole at S equal to S1, then E star of S must have poles at S equal to S1 plus J M multiplied by omega S, where M is equal to 0, plus minus 1, plus minus 2, etc. And to prove that, if E of S has a pole at S1, if E of S has a pole at S equal to S1, then E of S minus J multiplied by N multiplied by omega S must have a pole at S minus J multiplied by N multiplied by omega S. And this is the same as saying, if I call this S1, S is equal to S1 plus J multiplied by N multiplied by omega S. Now, since E star of S is equal to 1 over T, the summation from n negative infinity to infinity, E of S plus J multiplied by N multiplied by omega S, it follows that if E star has poles at S equal to, it follows that E star will have poles at S equal to S1 plus N multiplied by omega S. Okay. So I hope this is clear. If I have if E of S has any pole at S1, if I take E of S minus J in omega S, then S minus J in omega S is gonna be a pole, because E of S1 is a pole. So when S minus J in omega S is equal to S1, that is going to be also a pole. And therefore, when S is equal to S1 plus J in omega S, that is going to be a pole. So using this, since E star is equal to 1 over T, the summation of S plus J in omega S, it follows that if S1 is a pole, then S1 plus N omega S must be also a pole. Okay, just to illustrate this, so if I have E of S 1 over S minus P1, then I have a pole at when S is equal to P1. If I take E of S minus J in omega S, this is going to equal 1 over S minus J in omega S minus P1. Now in this case, this is the pole, or the denominator is equal to 0, then S is going to equal to P1 plus J multiplied by N multiplied by omega S. and this is, you know, this expression here. Okay. Okay, we're gonna I'm gonna stop this module, and we're gonna continue with the next module, looking at the pulse transfer function. Now, again, before I end this module, I realize this is lots of math and lots of derivation. Nevertheless, I mean, the key takeaway from all this derivation are these three expressions that we said we're going to derive. And these are the ones that we're going to be using and that we want to get out of all this derivation. Please try to, again, these are the key takeaway from this E star of S, and this is what we're going to need for the rest of the course. Please look at the derivation, make sure it looks familiar, make sure you can go through it. If you have any question or you feel like you're stuck understanding something, please by all means let me know, and we can schedule a time and we can go over it, or I can help you with any questions that you might have. Again, it's very heavy, lots of math, and some of it is not very intuitive. Some of it is, some of it is not. So if you feel overwhelmed, it's okay. It's probably, you're okay. Okay, thank you.